Hello, this one's about biasing a simple transistor amplifier, a single transistor stage, just using a transistor and 4 resistors. It's one of the commonest and simplest transistor amplifier stage circuits, and it's used all over the place. But from what I've seen online, there's a lot of people don't understand how to work out the resistors to use with it. This video is about working out resistor values so you can get a working amplifier without a lot of hassle. Now I'm going to switch to working on the PC using screen recording and easy EDA, because I can actually put text in and change things a lot easier than writing on here and scribbling things out. So this is now on the PC. I'll move that out of the way so we can use the mouse. Right, okay. So the principles are the current is set by those 2 resistors, or the maximum possible current is set by those 2 resistors if the transistors turn fully on. And of course, if the transistors turn fully off, there's no current through those 2. If the transistors turn on part way, so that the collector voltage is somewhere around half to 2/3 supply, then any change in the base voltage will cause a change in the voltage on the emitter resistor. Then the change in voltage across the emitter resistor will be reflected in the change in the voltage on the collector resistor in proportion to the resistor values and the current through them. Now that might sound complex, but in fact it's very, very simple. Say you've got a 100 ohm emitter resistor and a 1000 ohm collector resistor. For any given current within the possible range, the voltage across the collector resistor is going to be 10 times the voltage on the emitter resistor. And seeing the emitter resistor voltage is going to track and kind of emitter follow mode from the base, as long as it stays in a linear range, you have a 10 times gain amplifier. E.g. 1 MA through that is going to create 100 millivolts at 1 MA on 100 ohms, and 1 volt at 1 MA on 1000 ohms. So the basic concept to set this up and have it working properly is decide the value of the collector resistor. Now that wants to be high enough so you're not taking excessive current through the transistor, but low enough so that whatever this is connected to, because remember this will have a coupling capacitor from the collector to the next stage, whatever that happens to be, the output impedance of this, or the output value of that resistor, should be at least 10 times lower than the input impedance of the next stage. So if your next stage has an input impedance of 100k, the highest possible value you should use for that is 10k, and preferably lower, say 4.7k or 2.2k. The higher the ratio, the less effect the loading of the next stage has on this stage. But obviously you can't go too far. You can't start using 10 ohm resistors in the collector on a small single transistor and expect it to do anything practical. This whole setup is specific for small single transistors that have high gain, 100 or more, possibly 300, 500 even. So the base current, which also flows through the emitter, doesn't have a really significant effect on the overall current through the emitter collector chain. Anyway, so say the next stage has an input impedance of 47k, just for the sake of argument. So that should have a maximum value of 4.7k, and I'm going to call it 2.2k. So let's say that 2k2. Now you want a gain of 5, or DC gain, because you can set the AC gain separately, make that higher. Say you want a DC gain of 5, so the emitter resistor wants to be approximately a fifth of that. So make it well, a tenth would be 220 ohms, so make it 470 ohms. So now the voltage across that resistor is always going to be, in round figures, 5 times higher than that. Now I'm doing this with a 9 volt supply on this drawing, and the idea is I can then build the circuit on a breadboard afterwards and show the actual voltages to see how well they compare to the theoretical ones. And it should be fairly close. It's not going to be exactly the same, but it should be fairly close. So to give the maximum signal range, the collector voltage wants to be somewhere between half and 2/3 the supply voltage, because obviously when the transistors turn fully on, you've got you've got 5 and 1 units value, so you've got 6 units of resistance, if you like. So you got in 1/6 of the total supply voltage, say 1.5 volts on that resistor when it's turned fully on. So the range isn't fully from 0 volts to 9 volts. It's from 1.5 volts to 9 volts. So that gives you 7.5 volts swing. So saying roughly 3 to 3.5 volts across that resistor gives you the best range. And for 3 to 3.5 volts you need 1/5 of that across that resistor. So 0.6 to 0.7 of a volt. The transistor will also drop 0.6 to 0.7 of a volt in its base emitter junction. So that means the base wants to be at about 1.2 to 1.4 volts. And that's where these two come in to set a potential divider, which set the base current with no signal, the base voltage with no signal, which in turn set that voltage, and that from the current through it defines that. So it all goes around in a circle, if you like. It's all interactive. So we want about 1.4 volts from 9 volts. Well, if it's 1.5, it'd be 1/6 of that. So you want just under 1/6, about say 1/7. 56k and 10k as a ratio. That should be somewhere around right. Rounding that to 60 and 10, that gives you about 1/7. Now, so it's a bit somewhere around that. Anyway, that uses a calculator. 47k, 56k and 10k, or you could go a lot, you could multiply up from that. I'm just doing mental calculations. So say the transistor's got a gain of at least 100. Yeah, I wouldn't go above 100 times that value for that resistor then, just as a ballpark figure. So you don't want to go above about 47k there, and you want about 5 times higher on that one to make it 1/6. No, not 1/7, 1/6. So yeah, for sake of it, I'm going to make that 47k, and that about 5 times higher. Well, that would be 250k or just under, so make it 220. Again, it's approximations, but that should give a somewhat reasonable voltage on the base of the transistor to make it work in a linear range. Without using odd values, it may not be exact, but sorry, I've got a dry throat. It may not be exact, but it should be near enough to put it in a decent working linear range. Now, if we actually start calculating things, just out of curiosity, just work out the exact voltage I've ended up with on there to see how good my mental calculations are. So I've got 220 plus 47. So it's 9 divided by that, then times 47. 1.58, about 1.6 volts I've got there. According to that, which is a little bit higher than I meant to have, but let's see how it goes. it will be loaded down fractionally by the base current. So 1.58 volt there, that's near enough 1.6, so there's going to be almost 1 volt on that, so about 5 volts on that. So it will be well within the linear range still. There's a little bit of overhead for the signal. As long as the signal is not more than a couple of volts, it should still work fine. Now that resistor could be a bit higher, or that one a fraction lower, to get it nearer 1.2 to 1.4. So I mean, I don't know what it would be like with 270k there. Go back to the calculator. Oh, that should be better. 270k give 1.33 volts. Okay, so let's make that 270k then. That's in the range I was originally aiming for. Right, okay, so 1.33, that's going to be about 0.73 on the emitter and about 3.5 volts on there, which is about ideal, I'd have thought. So okay, let's try that in practice and see what voltage it comes out with. Assuming I can find the correct value resistors and don't headbutt the microphone too many times. I've not a clue what I've got on this. It's just some random bits that were in it before. Of a transistor. That's a 220k. I haven't got any values I need there. 470 ohms. 2.2k. 47k. 270 is not one I use very often. Okay, this might take a while. Okay, bulk resistor box time. Have a dig through here. This has got all the values that I don't use regularly. Right, I'm just going to confirm that because the bands are a bit dark. Yep, 270. It's the 47. I'm sorry. Okay, let's double check them. 47k. Cool. 268, 270k. 2.2k and 470 ohms. Right. Also, I don't know offhand what this transistor is or what the pin out is, so I'll just check that. Okay, so that should be emitter on the left, base in the middle, the collector on the right. So these bandoliers, so I'll trim the ends because the ends are sticky and they will mess up a breadboard. So 470 ohms emitter to negative. I'll move that up one so we've got access above and below it. K2. collector to positive. $47K base to negative. So assuming I've not messed up the transistor orientation, which is not impossible. And then 270K. This is literally old stock. It's probably about 30 years old, this one. Base to positive. A bit closer, can't it? Then I need 9 volt power, which will just take a minute to organise. Right. That's the battery connector. Just trim those back a bit. The ends are tin, so hopefully they will push in. If not, I'll have to re-tin them. Oh yeah, looks like my connector. Might not be a very solid connection, a bit thin, but let's see how it goes. This new battery connector is very stiff. Right, voltages. See how it ends up. So on DC voltage, put a negative on that point there. So the base voltage, let's see what the positive supply is. 9 volts almost exactly, okay. Base voltage, 1.33. It's just what was calculated. Emitter voltage, oh no, something not right there. The transistor is not conducting, so I've got something wrong on that transistor connection. Either something's not in properly, or in fact no, I'll get another transistor rather than messing around, because that was arranged for a specific setup. Okay, that's a new one. I'll mess about looking up online. I'll just use that tester again to see which way around it works, which is which. So one's collector of that. Okay, so that's going to be emitter, base, collector in that order. So emitter's on the left, base in the middle, collector on the right, which is what it should have been last time, but the leads were all skewed up. So base voltage, now that's gone down fraction now because it's drawing current. It's 1.2. In fact, now it's drawing current, the battery voltage might be dropping a bit. Yeah, the battery voltage is dropping a bit, so it's going to be varying all the time. But the emitter voltage is at 0.6, which is about what we're aiming for. And the collector voltage is 5.9, just under 6 volts. That's about 3 volts from the supply, which is again what we're aiming for. So that should be working as a linear amplifier with a gain of about 5. If I can actually connect it up to work, see what bits I've got here. The scope's got a flashing red light on it. Oh, it's a Handtake USB module, so I don't know if that's actually working or not. All I can do is try it. Yeah, I see it thinks it's working, yes. Okay, might be okay then. Right, so periscope probes. Ground them on the resistors there. This is going to be on the base, channel 1. On channel 2 on the collector. That resistor away a bit, so I've got a safe amount of space. The probe for the function generator output. Which should be set on ×1, so it's just giving a direct signal rather than going through a very high value resistor. Now, I need a coupling capacitor to the base. Just going to be a little bit fiddly to connect. Go there. So that's going to be the signal input to the base. Again, it's going to earth onto one of those resistors down there, and that's there. Now this isn't powered yet. I've got to plug it into the USB power bank. Okay. I'll set this gadget for say, I don't know, 1000. All the way, right. Right, that should now be producing a 1 kHz sine wave. And the scope is set on microseconds. There we go. Right, I'll just set that up a bit better. Right, oh, that's too high an amplitude for it. It's clipping a bit. Just turn it down. So now this is, oh, it's on 2 volts a centimetre as well, which is a bit high. Set them both on 1 volt per centimetre. Then you can see the respective range. Also set channel 1 to AC so that it's not. No, I'll leave it on DC. Set that down. Yeah. Set that down to 0. Set that down to that. Oh, in fact, I set them both to 0 because they're both on the transistor connections themselves, so they've both got DC offsets on. So you can see there's a lot of difference. I'm going to have to actually move that one down a bit. No, I can't move it negative. I've turned the gain down a bit as the range is just too high. But I think you can clearly see that it's inverting and giving a gain. Well, looking at that one, the signal on that, if I just play with that slightly, oh, that one, remember it's on 1 volt of division, so that's at about 0.8 volts roughly, and that one, the output is more or less symmetrically in that, so it's about 4 and a bit volts. So the gain is roughly around 5 as it's calculated, and you can see as long as the signal level is not too high, it is giving a nice sine wave. If you go too high, then it will be clipping. It'll be running out of range at the top or the bottom. If you go silly high, you can see it's running out the range at the bottom. Now if I change the coupling to AC on channel 1, sorry, channel 2, the output from the collector, so it's centered around 0 rather than, that's just confused the scope whilst I've changed the gain. Right, so that you should be able to see the distortion start to appear then. If the biasing's about right, it should start to kick in more or less symmetrically. So it's quite a high signal at that. When it starts to distort, it's 1, 2, 3. It's in excess of 6 volts output swing before it starts to distort. Then it kicks in. It starts to distort at the positive side first. Then you can see it's just starting to clip at the negative side as well at that. So there's not a lot of imbalance. In fact, if I set that up now, so we've got almost exactly 1 volt input. And in fact, I can change channel 1 to AC as well. So that's centered around. And the mouse is off the edge of my mouse mat, which is making it difficult to move things. Set that to 0 as well. The waveform's obviously a bit lumpy just from the screen display, but with that set to roughly positive and negative half a division on screen, let me just have that. I don't know where the trigger. That's why it's drifting. Let's just get rid of that drift. We can move the trigger into range. Right, let's go. A bit better lock. Okay. Maybe not. Right, so as I was saying before, I think it's actually better with it drifting. So at least it's not kicking like that. Okay. As I was saying, with about plus or minus half a volt there, so 1 volt to peak there is 1, 2, 3, 4, 4.5 volts probably out. Yeah, I mean, it's difficult to judge the exact voltage there, but it's pretty close to 5 times, as it should be. And you can see it has got a good linear range. It's up to in excess of 6 volts peak to peak output voltage on a 9 volts or supply, or probably a bit less now, the battery's under load, before it starts to clip. So hopefully that's something useful. If you are designing small signal transistor stages, that will be helpful. Now the next thing I mentioned earlier is that the AC gain can be much higher. The DC gain needs setting to work out the bias values, and you can't really go very high on that because the resistor value ratios and the possible swings, the emitter voltage starts to get too low to be stable and guaranteed to work. So you want to keep the DC gain down, but you can put the AC gain up by shunting the emitter resistor with another resistor and a capacitor. If I go back to the drawing and add in, I'll just copy that, not bother about values. Add in another resistor and the capacitors on it. Out of the way again. So another emitter resistor, but with a series capacitor of a high enough value that it's not going to affect the frequency response down to the lowest frequency you want the amplifier to work with. Now because that's the same value, at AC the value is half, so the gain will now be 10 rather than 5. If I made that 220 ohms, the gain should be about 20. So make that 220 ohms. Sorry, no. Sorry, it's, no. If the overall value was 220, both, if they're both 220 with that. If I want it to, remember it's resisted in parallel, so I need to go down to about 100 ohms. So 150 ohms is a ballpark figure. I don't know the exact ratio, but that should be somewhere around a gain of 20. So see how it works. What value this capacitor is? 47 might, not 100 might, but that should do. So that's going to go in positive to the emitter, which is there. And then I need a 150 ohm from that to 0 volts negative. Yes. Right. So 150 ohm. Again, it's been bandolier, so trim it, get rid of the stickiness. And that wants to connect from the other side of the capacitor back to 0 volts. That there. Okay, now switch back to the scope. The gain now should be more like 20. Connected it correctly. Or if the capacitor is too small. If the capacitor is too small, it'll cut out low frequencies. Yeah, that's about 1 volt into. No, that's not having any effect. There's something not right there. Right. Bigger capacitor. That's 1000. You can see that did have a fractional effect on the gain, but not a lot. Just equalise the lead length on that. There we go. That's better. As you can see, the gain has jumped up quite a bit. It's not up to 20. I think my mental calculations might be a little bit off, but as you can see, it's a lot higher. The maximum voltage output is still, of course, the same, because that's when the amplifier starts to clip. It runs out of voltage range. And that's what happens if I go down a bit more on that resistor. Try a couple of lower values just to see the effects. So for 100 ohm, these both sticky ends. So 100 ohms. Mm-hmm. It's almost like that 150 ohm resistor wasn't 150 ohms. That's gone way, way higher. Ah, no wonder. That's that wasn't a 150. It's a 750. The first band's purple, not brown. That because of the colouring on it, it's a bit difficult to read. That's why the gain didn't go up as much as I expected. Okay, so that's with a 100 ohm resistor. You see the gain is now massively higher. I have to change the channel 1 gain a bit, I think. Right, that's now 100 millivolt range on the input to 1 volt on the output. So yeah, the gain is over 20 there. You can see it's twice as big and 10 times difference in scaling. So the gain is well over 20 at that. If I change that down again, that's the 33 ohm I got. So that's back to the original 5 times gain. You can see the output's now about half the input with a 10 times offset. So wrong track. Now that's now 33 ohm, which there's a lot of noise. It's just because of the general surrounding USB power and things. Again, it will clip if we go too much. You can see it's starting to get a little bit asymmetric as well as we get near full swing, because the pull-up value, once it gets very near the positive, has very little current. You know, the collector resistor, as the collector gets near the positive rail, there's very little current available, so it doesn't respond as well. But as long as you keep the voltages reasonable, it's quite linear. And so the noise is, I don't know what that's from, it could be from anything, but that's not part of the amplifier itself, it's from the other equipment around here in the computer and things, or you could even with the USB, something switch mode devices in the USB power. Anyway, so that's with a 33 ohm resistor, and the gain is now looking like it's about 30 or so, 30 to 40 range. It's difficult to see exactly. Yeah, I would say that's roughly 1 division peak to peak on the yellow trace, which means it's about 100 millivolts, and it's near enough 4 divisions peak to peak at 1 volt per division, so it's 4 volts. So the gain's about 40, just from a single transistor stage. So you can see how you can change the gain at AC audio, or all the frequencies depending on what you're working with, as long as the coupling capacitor is big enough that it's not a significant impedance compared to the extra emitter resistor at the frequency you're working with. Obviously, if you use a 0.1 cap, say there, then the low frequency gain would roll off quite rapidly, because that's got a very high impedance at low frequencies. That's now, at the moment now, I've now got a 1000 microfarad there, which is probably a bit excessive, but there again, it's now down to a 33 ohm resistor, so it may not be. Anyway, that's the principles. That's still the basic circuit, just with the extra capacitor and resistor added, and you can see it does amplify quite nicely, and the DC voltages are pretty close to the theoretical values, just from a very simple calculation. So I hope that's of use, and thanks for watching, and please subscribe if you enjoy the content and like to see more.